I just unplugged my refrigerator for you, so pay attention, okay? Um, these are the Einstein field equations. Uh, when I first learned about relativity, the thing that was so pronounced to me was obviously the nonlinearity of relativity and how that comes from the constancy of the speed of light. And so that was kind of the theme I learned about Einstein, was that was that was the thing that intrigued him also. But he also had this idea about the equivalence principle, and so he wanted to apply this nonlinearity to gravity. And so that's how he came up with these Einstein field equations. And so this is the way I've always kind of thought about it. Like the left side here, the G, what looks like a UV, that's G mu. It's so ridiculous. Anyways, that's the Einstein tensor, and so that's the part that encodes the nonlinearity of relativity and the constancy of the speed of light. And then the right side is the stress energy tensor. And so this first one, these are the same. And this is in natural units, and so there's different forms of it, but this is the most elegant form, is this first one. And this one down here just shows the stress energy tensor. And these tensors, if you don't know what math is, if you're like me and math is just, it's not that big of a deal for you. like I am terrible at math. That's why I mean it's not that big of a deal. It's like I don't give a shit about math. It's so stupid. But regardless, there's a lot of math people, and then there's people that don't know anything about math. If you don't know anything about math, a tensor is kind of like a vector. And hopefully you kind of understand what a vector is. A vector, so you have scalars, vectors, and tensors, and rank 2 tensor. And so a scalar is like it's like 4. It's like you're saying 4, nothing. Like there's no units with it. The 4 is, like I don't really know if pi is a scalar, but there's things like that don't really don't have, they can have, you can have like 4 kilograms, I think that, but it's not like there's a direction, whereas a vector is like you're going somewhere. There's a direction and a magnitude. So it's like got all this other stuff attached to it that you have to keep track of. There's energy conservation and things like that you have to maintain throughout all these. And then you have a tensor, which is like like a matrix or matrices. And a rank 2 tensor is like you have another degree of freedom with those matrices. But it's basically, it's, to me, it's the same damn thing as a vector. Now math people will go crazy, but that's the way I've always thought of it. It's just this, it contains all of this information. And then they write a symbol and then they call it a tensor, a rank 2 tensor, and they think they're cool. But regardless, that's what this is. So that's all this represents. And like I say, the left side here, the Einstein tensor, that is the part that Einstein was searching for. The story of Einstein is that he had this great insight in relativity, with special relativity. And this insight was that if the speed of light is truly a constant for all observers, then there are these serious consequences that arises from that. One of those is that everything is relative. Like everything is based on a relationship with another. There's nothing that is set in stone. There's no definite point in space and time. And so this was a great insight to Einstein. And he, it worked out marvelous with special relativity, but like He always had this idea of the equivalence principle in mind. And so that's why, that's what he was searching for, is a way to do, like, this was the part that was difficult. This tensor stuff was hard. And so, like, he wanted to be able to duplicate the conservation of energy and the nonlinearity of special relativity into this tensor. And that's what he accomplished it. And the stress energy tensor shows it's the distribution, it's the matter content. It basically includes everything. Okay, and so to have a solution to these equations, you have to satisfy both sides. So it's a little weird, but you have to be able to satisfy this side and this side. And you do that through a setup. Basically, you're saying, all right, I'm going to do this. And so the most basic setup is the Schwarzschild solution. And so basically the Schwarzschild solution is this. So basically you have a spherical symmetrical ball. It's a spherically symmetrical ball. You can have, with the Schwarzschild solution, it's kind of unique in that there's, so long as you have spherical symmetry, then it's as if all of the mass is in the center of the object. Now, all the geniuses in the room will point out that the Schwarzschild solution is a vacuum solution, and it doesn't represent the real world. To those people, this is what people say when I present no, people don't respond, but a few people have. And, one of the things that they always like to say is that the Schwarzschild solution is a vacuum solution. And see, to me, that vacuum solution, that's so nonsensical, because there are no real models. All models are inaccurate. There are only useful models. Some are more useful than others. There's a quote there, and I don't know who said it or what the quote is, but the idea behind it is amazing. All of these mathematical models that they create are inaccurate. They're not true. Okay, they're definitely, like, that's what you have to understand, is that we can't map reality perfectly. We do the best we can to estimate. And that, especially when you're talking about general relativity in a solution. And so I use tends toward. It's not, the Schwarzschild solution is not the perfect solution to use, but it does tend toward that when you have spherical symmetry. This is basically with everything. The Newtonian gravity is just it's kind of accurate. You tend toward it. I don't know, but the experts get a little foamy at the mouth with this stuff, and their eyes glaze over, and they think that they're so much smarter than everyone, but they're really just repeating the same nonsense that everyone else has been repeating, and we're going to get into that. So they believe that instead of spherical symmetry, that they can just declare the universe as homogeneous, okay? And strict homogeneity is obviously false, because strict homogeneity is... I'm sorry, I don't know what my dog was whining about. I do. My cat jumped up on the kitchen counter, and my dog was like, get down, get down, get down. Regardless, we're talking about homogeneity and how useless of an idea this is, okay? To solve these solutions, to be able to satisfy the field equations, you have to have symmetry, okay? You have to choose a symmetry. The reason you have to choose it is because it's complicated, and this makes it easier. Well, Friedman and all the other goofballs, They just said, oh, well, let's just say that everything is homogeneous, because on the largest scales it is. And so they created these nonsensical solutions. Now, there's two problems here. The assumption of homogeneity is the it's one of the biggest, most glaring, obvious problems. But then there's this idea that the metric can expand. And this is another nonsensical claim. Space-time is not... I went over all of this. Okay, I had to go over the Einstein field equations because I want you to understand that space-time is not a physical thing that possesses properties of its own. The space-time is in the stress energy tensor. And it's a package that comes along. It's not even a package, okay? I'm like, there's a lot of people claim that the space-time is a box that you put mass in. That is false. Space-time is nothing, okay? Nothing. That's the definition of the vacuum. It is the void. It is literally the absence of things. That is the definition of space-time. The space-time inside the stress-energy tensor manifests as a relational thing between other matter and energy. So it's a measuring apparatus that humans attribute to the matter, okay? The matter comes with these units. The mass and energy and space-time are all intertwined together in a single thing. You can't separate them. I mean, you can, because we can do whatever we want. We define space-time, but the relationships between the mass and the energy is defined by the physical properties of those things, whereas space-time is defined by humans. We define it as as numbers. So I'm starting to ramble. Let me get back on script here. I get a little... This is the part that I'm most passionate about. We don't see expanding space until the FLRW nonsense, okay? The Einstein field equations and the Einstein the Einstein universe, they don't have expanding space. Expanding space is not a part of general relativity. I've heard lots of people make this claim, and this is infuriating, that there are professors out there saying that expanding space is part of general, or it's predicted by general relativity, or it's it's within the same theory. It is not. It is absolutely, you can, like, I will fight to the death over this one. Expanding space is a separate theory from general relativity. General relativity does not cause space to expand, okay? General relativity is a set of field equations that you must satisfy. By saying that something is expanding space, you're toying with the ability to solve those equations. You're walking a tightrope in order to make it easy for you. This is exactly what the scientific method tells us not to do. Okay? With the Friedman and the FLRW metric, we obtain this thing that is called a scale factor. They really, the nutballs go nuts over this. They act like it's perfectly fine, that this doesn't violate general covariance. But essentially, it's what they've done is they've created a new definition for mass density. And this definition of mass density violates general covariance, which is the main core of general relativity. And so general covariance is just this idea that All physical laws are the same in all frames of reference. No matter what coordinates you choose, you have to use the same damn equations. And the reason that we have all of this amazing stuff in the universe is because of this thing called general covariance. Okay? It's literally relativity. Okay? The space-time is only real in the same sense that proper names, laws, gender, and boundaries are real. These are imaginary lines drawn by human. Sure, they represent real physical things, but they are representative. They are not the things. They require a code. There's a code that the humans follow to be able to deconstruct the representation from these abstract concepts. Space-time is one of those things. It's like currency. Or it's like your full name. It's not a physical object. I think I've already went over this. The stress energy tensor contains all of the space. It contains the relationships. And so this space-time is not an emergent property. It's encoded in the relationships. Okay? It's not encoded in the relationship. I guess that's we mapped our abstract numbers onto the relationships to help us keep track of the relationships. But it's not, space-time is the absence of things. Mass density. Take the equation for mass density, for instance. Mass density equals mass divided by the volume. Volume is not a real physical thing. It's a geometrical concept. It's how we choose to measure where the mass is. It's a human choice. It's like saying, hey, we're talking about this mass right here, not that mass over there. It's purely a coordinate choice. This choice cannot impact the physical world. It's crazy that I have to explain this. But the same thing, this same problem exists in expanding space. You can define space as expanding if you want. It's fine. It's going to make things very complicated to keep track of. It's even a physically realistic thing, okay, to say that things are expanding, but typically it would be that a region has undergone some cause to expand, like an explosion. Then you could introduce some scale factor that would describe the relationships of the particles and how they evolve over time. But with the current method of space-time expansion in the FLRW metric, it's as if the mass density is deteriorating, it's decreasing every day. It gets lower. This nonsense may have been, I don't know what I wrote here. This nonsense may have been remained acceptable to the community, but fortunately the discovery that this deteriorating is, this nonsense may have remained acceptable to the community. Yeah, my point here is that if they had never discovered dark energy, quote unquote, if they had never found out that it was accelerating, then it could have just been that everybody been like, oh, okay, this is acceptable. We have a good thing now. This works perfectly. Now, they're still like that, but at least after the dark energy controversy, then everybody's saying, why is it accelerating? Because that really doesn't make sense. Accelerating expansion is stupid. It really does not make sense. Before that, expansion really wasn't questioned. And there's a thing. Let me see. I'm off track a little. This is exactly why scientists are so okay. Yes, I understand the point I was trying to make. I did a piss poor job writing this script, but the whole reason. Now, there's a couple reasons that they think that the universe is expanding, but if you follow the history, if you go back to Einstein's original universe, like he tried to formulate a cosmological solution, and he intuitively thought that it would be static and stable. It wasn't. It's notoriously unstable. It's been described as being equivalent to balancing a needle on its. For some reason, I always want to say its head, but that doesn't make sense. It's the point. You could actually balance a needle on the head if the head was kind of flat. But anyways, it's like balancing a needle. It's and that's because he included this thing called the cosmological constant. And that's because the reason is because he assumed the universe would collapse. And that's because he used a homogeneous mass density. And this is what sucks, is that Einstein made this mistake. Einstein made the mistake of assuming the universe was homogeneous. This is a fatal error. The universe is not homogeneous. It does not collapse. Okay? If you formulate the solution, it does not tell you that it collapses to a single point. Because if it's homogeneous, it cannot collapse to a single point. You have to have an inhomogeneity to begin the collapse. Any inhomogeneity violates your notion of homogeneity. So you don't need a cosmological constant. The equations tell you what it does. It does nothing because it's homogeneous. Any collapse chooses it violates the Copernican principle. The Copernican principle is the idea that you can't just choose a point and say that this is the center of the universe. All points should be the center of the universe. And if all points are homogeneous, and if all points are the center of the universe, then the universe is collapsing towards all points, and you just described gravity. This is not a cosmological model. Homogeneity is not a real concept. A collapse has a gradient, a center of convergence, and a violation of symmetry. So you have to have some place for the shit to collapse to. Once you choose a place for this shit to collapse to, then you're violating the Copernican principle. All of this nonsense led to the FLRW. They're like, oh, well, if the universe is either collapsing or expanding, because Einstein, to prevent it from collapsing, he used a cosmological constant. And the cosmological constant is just another nonsensical bullshit term added in because you would expect the universe to be stable. It's not going to collapse to a single point. This is obvious because we're here. And so you need to keep it going. So he just added a term. Whatever is keeping it open, that's the term. It's technically accurate. It's the interpretation that's wrong. The interpretation that space expands or that there's any kind of vacuum energy, this is just terrible physics. This is from fraudsters repeating what their fraudsters told them. And then the fraudsters are out there lobbying to protect the fraudster industry. So what gives? Does the model violate the principle? Is there a category error interpreting collapse? Yeah, it's not a physically real model. It's a solution to the field equations, but it's not physically meaningful. Co-moving coordinates don't change this, okay? You can't go, this is why it's important not to conflate general relativity and co-moving coordinates. Co-moving coordinates are not part of the Einstein universe. The co-moving coordinates are the Friedman equations, okay? This is not the Einstein universe. Also, the co-moving coordinates don't change momentum of objects. Momentum is conserved in the co-moving frame. How does the universe collapse or expand? The answer is that it doesn't. Collapse and expand is purely a metric coefficient AT. And so I'm talking about the Einstein universe here. The collapse is purely in the metric coefficient. Any change is of the matter's momentum. It does not change the matter's momentum. Okay, the coordinates don't cause it to collapse. You're just choosing different coordinates. Especially if it's homogeneous, because there's no way to tell any difference between any other region. Every region is identical, so you can't tell if it's collapsed or not. There's no local gravitational pull because it's homogeneous. There's no velocity gradient because it's homogeneous. There's no force because it's homogeneous. In addition, the collapse only happens if there's inhomogeneous. Okay, I've already went over this. I'm starting to repeat myself. So how do we fix this shit? That's the question. Well, you use a real density profile. You've got a narrow range of options. You've got 1 over r. You've got 1 over r squared. You've got 1 over r cubed. And everything in between. And those are essentially our only options. There is no other option. Anything else is not realistic, or you can't match reality. Okay? Once you have a real density profile, like we're talking about a real one, then now you suddenly can produce a distance proportional redshift. The gravitational redshift allows this. Once you get rid of homogeneity and you use a real density profile, you don't need an explanation for the cosmological redshift. Guess what? There is exactly one density profile that can both reproduce the CMB temperature through Hawking radiation and the Hubble constant. That profile is rho equals K over R, where K is 0.833 kilograms per meter squared. This is very important. This K does not come from nowhere. This K is exactly 2 times the surface density of the horizon it creates. So these questions of stability that arise when you talk about a distribution like this or a static universe, there's all these questions of stability arise because of this history of the Einstein universe and the Friedman metrics. You have to understand that if there's no reason, or if there's no evidence the universe is expanding, in other words, we have an explanation for the cosmological redshift through gravitational redshift. If we have an explanation for that, There is no evidence the universe is expanding or collapsing. Also, there's no evidence the Einstein universe would collapse because it's a homogeneous universe. That's not a realistic profile. When you use a realistic profile like this K over R, you suddenly have a scale dependency. And so the genes argument and all of these perturbations that cause collapse, they're suddenly corralled into their own scale. So yeah, sure, you can throw a giant fireball at a galaxy. It's not going to collapse the whole universe because the perturbations are scale dependent, just as everything else. And there is no center. There is no chosen center. All points are the center and the horizon. Okay, everything is, there is no geometrical center or edge. It's a relational horizon. The horizon is relational. I'll just read this last part. Perhaps my strongest argument with all of this is that equations, all physical equations, have a built-in scale dependency. And mainstream physics does not adhere to this. This is a strong argument. Mass density is a scale-dependent variable. Gravity, mass, density, pressure, energy, all of those things have some sort of unit that comes along with it that expresses the dimensionality of it. If you disregard these units, you disregard all of our basic physical laws and all of physics. Mass density is a scale-dependent variable. Vacuum energy density is a misnomer. The real question is, what is the minimum gravitational energy density at some scale? The vacuum does not exist. That's literally the definition of it. I'll leave you with that. Y'all have a great night.